Recording is rolling. So today is Monday, October 17th. We're in the middle of, well, we're getting closer to the end of doing centripetal force, which is one of the recent labs you guys did. We're going to combine that with universal gravitation, make orbits, the whole deal. Right, so I put together your guys' quiz over this last weekend, and some of the questions I liked a lot were actually from conceptuals, from my conceptual class. So there's, you guys see this half page on your desk? It was on your desk when you guys walked in? Right, so this is nothing you guys have to turn in. This is just extra notes for you guys, but these are the questions that are going to show up on the Kahoot that we're going to do today. Okay, they're all in order, right? And some of these questions are going to show up on your quiz when I eventually get to you guys later this week. Okay, so that'll help you guys out there. That's just extra notes for you guys. Right. Oh, also on your desk when you guys walked in was this page, which I had forgotten to print earlier, but you guys have it now. I mean, it's been on Google Classroom, but you guys remember I assigned these problems to you guys. Right, so these problems I do want to cover with you guys tomorrow. Right, so that's the tomorrow plan. You're gonna cover whatever problems I find from this page, right? And then also your guys' chapter 7 page, right? So that is tomorrow's adventure. There we go, chapter 6 and 7 problems right there. Oh
Do you
yeah.
have an extra chapter 7 that was part of the video?
Chapter 7. There you go.
Thank you.
Yep. All right. Anybody else has missed anything? Remember, I've got a couple extra copies here. Everything's on Google Classroom. All right, so tomorrow we'll do as many textbook problems as we can. I do have some extra demos and whatnot lined up for the next couple days. Okay. Thursday is gonna be a flex day. I do have always more problems I can solve with guys, more demos here and there. Right, so see what I need to cover by then. Okay. And then Friday I do want to end this whole unit with a lab that's similar to what we started with. It's a centripetal force type lab, right? Which is how we started this whole unit a while back. And so we're gonna break out the turntables on Friday. Man, have you guys calculate what's the coefficient of static friction between like some object and the surface, right? Right. So that is what we're looking at this week. Now, before we jump into the Kahoot, let me start with warm up with a few things. We're gonna start with the Paul Hewitt video. Now, pay close attention to this Paul Hewitt video because it's gonna be a setup for some of the things that are about to be lined up here. Some of you guys are logged on to Kahoot. That is awesome. All right, let me find Paul Hewitt. Here we go. All right, so inside a hollow planet. Oh, hold on. Let me mute that Kahoot. Oops. Mute Kahoot. Where's? There we go. There you go. All right, back to Paul. Where's Paul? Here's Paul. Okay. So let me start with this. If
would have no.
Okay. Guys, suppose you have a solid planet and you tunnel a hole all the way down to the very center of the planet. Can you guys, everybody look here. Okay. Think deeply about this. Okay. If you tunnel all the way to the center of the planet, now let's ignore the fact that it's all molten and blah, 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 right? Just focus on the gravitational effects. Just assume simplification, it's like constant density all the way down to the center, right? And you tunnel down and you find like a cave right at the center of the planet. Okay. Because what would it feel like to be hanging out right at the center of the planet? And I'll narrow it down to 2 options. Would you be floating around like an astronaut, or would you feel very, very heavy? What would it feel like? And let me see a show of hands. What you guys are thinking? How many guys think that right at the center you would be floating around like an astronaut? Who thinks that? Floating around like an astronaut. All right. Yeah, there's my winners. All right, right there. Yeah, you guys are right. All right. Now, what would it be? Well, can you guys imagine that every single grain of sand on Earth would be pulling you in a different direction and it'd be sort of like canceling out, right? Another way to think of it is like, well, where would the floor even be? Like, what would you even be standing on? Like, if you felt very heavy, you're talking about a very large gravity force, but which direction would that even pull? Well, it wouldn't, because all the directions cancel out. Yeah, you'd be floating around. It would feel like a gravity free. All right, now here's a new scenario. He's about set. It's like, what if you're exploring the galaxy and you come across this planet and you're walking around on it, and you start to tunnel down, and you realize, oh, this whole planet is a giant eggshell, right? It's a giant eggshell of a planet, right? You step inside that planet into like this chair. Okay, now what?
Gravity, because it'd be pulled in all directions equally. Do we see that? But what I want to do is I want to convince you that it would cancel out no matter where you are. And so what we'll do is we'll take a point that's about here, where this distance here is twice this distance. Do you think it would still cancel out this side and this side? What we'll do is we'll consider a solid cone of material. We'll call this M1. We'll call that D1. We'll call this M2 and 2D. Well, just D and 2D. Let's look at our equation. Let's have the equation guide our thinking, gang. The force over here would be our mass, say the mass of the point, okay, times M1 divided by D squared. That's this force. The force that's pulling over here, you might think it's more because it's more mass. Or you might think it's weaker because it's further away. And guess what one does to the other?
Yes, guys, look at the you guys see this this shell on the left compared to the shell on the right, right? The fact that the one on the left is twice as far away, right, compared to the one on the right, you think it has like twice the diameter? But twice the diameter, that translates to what times the area?
4 times the area?
4 times the area, right? 4 times the area, therefore 4 times the mass, right?
See, when you're out here, it'd be twice as much this way, but twice as much this way. So how big would M2 be compared to M1? Do you see it's 4? It's 4. So M2 would be 4 times M1. That'd be like 4 M1s, boom, times your mass, MP, divided by this distance here, 2D squared. But when I take the twice the distance and I square it, what do I get, gang? Isn't it like 4D squared? And what do the 4s do? And what's this? The same darn thing I got here. So you know what? The pull here, equal. I just took a place that was easy because I got twice the distance here as here. But you put any distance you want and that will happen. Anywhere inside there, there'll be no gravity. There'll be no field region. Inside a shell like that, there'd be gravity-free region. There'd be no gravitational field due to this mass. It would cancel out everywhere.
All right, so that's pretty cool. All right, so let's take that and extend that a bit. Right, ooh, I meant to flash these up here, but you guys see these posters taken from the ceiling anyway, right? Okay, quick review. We've got universal gravitation. Got some orbit Kepler's laws. Attraction predates Isaac Newton. Put it all together. Right, got orbital speed. The whole thing. All right. Okay, so you guys remember that. Oh, there's a scaling trick. Let's go back to a solid planet now, right? But you have that in mind. What happens with an eggshell? It's gonna help part of this process here, right? So we're back to just a regular solid planet. Okay. I brought my shovel. We're gonna dig a tunnel, spiral staircase all the way down to the center, right? Okay. Now you guys know, of course, right in the middle, you're just floating around like an astronaut. Okay. On the surface, you have some weight, right? And hey, what if you take off in a rocket and you start flying away? Okay. Well, you guys remember force of gravity between you and the planet. Here's the mass of the planet. Here's the mass of you. Okay. Well, universal gravity constant times the mass of the planet times the mass of you divided by the distance between the two squared. And you're always going from center to center. So from the center of the planet to like this guy in the rocket ship, some general distance, little r. Right. Or I could even do. Sometimes I try to save the capital R for like a fixed radial size, right? Like fixed radial size of a planet, capital R. Right. All right. Now I wonder, let's say just in general, what is your weight? Anywhere in the vicinity of a planet. Okay? So on the horizontal axis, I'm going to put some generic distance. This could be in meters, right? Where location 0 would represent the center of the planet, right? Location 0, center of the planet. Okay. And then as you go out, there's this very special distance right here, capital R. So I'll throw that right here, capital R. Okay. And then you could, of course, take off in a rocket and just like keep going. Okay. And then what are your resulting weights? I'm going to represent the capital F for force because you guys know weight is a type of force. I can measure this in newtons, right? Okay. Get so far with the space and the scrap. Now, we've all been stuck our entire lives at the surface of a planet. So we know that at the surface of a planet, you're going to have some weight. Usually I call it mg, so I'll just go and do the same thing here. Okay. So this is all any of us have experienced our entire lives since this point on this graph. Is that true? Okay. And we sort of worked out, well, if you were right in the middle, every grain of sand is pulling you a different direction, it all cancels out. So you would have 0 weight at the center of the Earth. Okay, so we got a second point, right? Now I wonder what the rest of this graph would look like. Okay. I'd like to give you more time, but trying to also save some class time. So how about this? Okay. start by taking off the rocket because that one's a little easier to figure out. Okay. You guys see this inverse square relationship between the force and the distance, right? So as you get further away, there's less and less force. Right? In fact, if you're twice as far away, right, this will show up later. Here, this could be one of the Kahoot questions that shows up. What if you were on top of a ladder that was exactly 1 Earth radius tall? You see capital R, another capital R. It walks the top of this ladder. So you're effectively doubled your distance to the center of the Earth. Okay. How much would you weigh up there compared to the surface? What's 1/2 squared? 2 squared is 4. It's 1/that 1/4. You have a quarter of your original weight, right? Okay. Huh. So let's see. 1/4 of your original weight. That's down here. So if you don't, that's right at the edge of the paper. It's like this. Huh. So your weight would be going down. Gravity force from Earth. Okay. In fact, you would be tapering off 1 the distance squared. See how it's like a kind of curvy line? Okay. You guys ever been in math class? Graph y equals 1/x squared. Looks kind of like that, doesn't it? A little piece of that graph. Right. Okay, so we're filling in this graph. Now let's go back to this guy with a shovel. And he's taking this tunnel, spiral staircase all the way to the center. Okay. Now here's where here, how about this? Okay. Remember, as this guy's walking down, let's say he gets like halfway down the staircase to the center, like just right there. I wonder what his weight is right there. Okay. Well, isn't it true that all the dirt above this guy in elevation is like a bunch of concentric rings? And we just, Paul Hewitt just showed that if you're inside like a spherical shell, that everything above you in elevation effectively cancels out and you're just floating around like an astronaut, right? So isn't it true that all this is it's like a bunch of concentric rings that cancel out? So effectively, so again, you're like halfway down the spiral staircase. All the planet that pulls on you, it's as if it's just a dirt ball that's only below you in elevation, which is like that, right? This. Okay. Now here's where the scaling comes in. Okay. Have you guys seen this yet? Oh, okay. You guys seen this? Okay. So where suppose you like have a little box, you triple one side of it, but you scale everything up proportionally. Okay. Well, everything that's linear goes up by a factor of 3, but the surface area goes up by a factor of 9. See, like 1 panel compared to 9 panels, and the volume goes up by how much? I see 27, right? 3 by 3 by 3. If you fill these with water, right, 27 times water, right? 27 times volume. Right. Now, how does that relate to this? Well, because this portion of the Earth that's left, right below this guy's feet, right? Let's see, if it's half the radial size, right? That would be 1/2 times 1/2 times 1/2 would be 1/8 of the volume. This little sphere here is 1/8 of the full volume. Right? We're talking about like a sphere, right? And isn't mass proportional to volume? Okay. So we got mass proportional to r cubed. And then the force is proportional 1/r squared. Okay. So wouldn't force be proportional to, let's see, r cubed divided by r squared, which is just equal to r. Right. So the fact that force to be proportional to r as you're walking down a spiral staircase, what that means then is that this is going to be a linear relationship all the way down. Okay. As long as you assume common density all the way down. Right. So if you're halfway down to the center, you'll have half your usual weight. Okay, so there you go. There's your weight in the vicinity of any planet. Okay? And the most you'll ever weigh is right at the surface. Okay? Next idea, I need to talk to you guys about tides. Right, tides and tidal force. Where is, here it is, here it is. Okay. Yeah, so what, right, leading into tides, how about this? Okay. What do you think there's a greater force from? Is there a greater force from the sun on the Earth or from the moon on the Earth? What do you guys think? Right, here's the Earth. What do you guys think of it? Oh, we're going to show hands here pretty soon. Right, here could be like the moon. So here's the Earth, here's the moon, and then way off in the distance is the sun. I'll do S for sun. Right, now this is not the scale at all, but it's close enough to make the point I'm trying to make here. Right, right. So the moon's pulling on the Earth one way, the sun's pulling the other way. Right. Let me see, show of hands. Which force do you think is bigger? Which force is bigger? How many of you guys think that the sun to the Earth is a greater force? Greater force. Ooh, bunch of hands there. Right. Does anybody think moon, Earth is greater force? Okay, so that one's got some votes too. Right. How about this? Which one has a greater effect on the tides? Which is the main driver of the tides? The sun or the moon? No, that answer is definitely the moon, right? Okay. So let's go back to the original question. We're going to paddle back and forth between these questions. Okay. I have mass of the sun, mass of the moon, mass of the Earth. distance from the sun to the earth, distance from the moon to the earth, and universal gravity constant. Can't I feed all these numbers into this expression and get, say, this force versus this force? We could do that, right? Okay. Let's do that. You know what? All right, this is a real good practice to do, right? Scientific notation practice, blah, blah. Here, I'll do one real fast. Let's do the sun and the earth. So force equals, here, I'll take this universal gravity constant, 6.67 times 10 to the negative 11 times the mass of the sun, 1.99 times 10 to the 30 times the mass of the earth, 5.97 times 10 to the 24, all divided by the Earth-Sun distance is 149 billion meters, right? Don't forget to square that. Okay. I'm looking at 3.57 times 10 to the 22 newtons, because newtons would be a force, right? Right. I could do a similar type setup for the moon, and here's the results, right? So from the sun to the earth and from the moon to the earth. Right. Now, do you guys see the answer to that original question? Who pulls with a greater force? What's the answer? Definitely the sun by a factor of like 100, because 10 to the 22 beats 10 to the 20, right? Right, by like 100 times. Actually, it's over 100, right? Because this is bigger than this number 2. Right? So over 100 times the force from the sun compared to the moon. Okay? Wait, so why is the moon the greater driver of the tides? Right? Well, it has to do with proportional distances from one side to another. Right? So the fact that Earth has a diameter and that one side of the Earth is closer to the moon than the other side. Okay? So all this F equals GMM over R squared, we've really been doing center to center distance. Right? But when you're doing tides, you have to think, well, there's one surface that's a little bit different distance from the other surface. Okay. You guys see like this in proportion to this, right? If you take that ratio, right, this divided by this is definitely more than 1. It's like 1.0 something, right? Okay. Now you could do similar setup for the sun and it'd also be like a ratio that's a little bit more than 1, but not very much. You'd be almost a 1-to-1 ratio from here to here versus here to here, right? Okay. It's almost exactly a 1-to-1 ratio. Okay. But the moon to the earth, that's a little bit more pronounced. Okay. Okay. The fact that there's a proportional difference there, that's the driver of the tides. And of course, greater proportional distance to the moon. That's why the moon is the greater driver of the tides. Okay. Let's do 2 more things for the Kahoot. Right. And you cover. Let's look at a special kind of satellite motion. This is going to be one of your Kahoot questions, by the way. Well, it's going to be related. Okay. So just got the Earth. Here's the Earth, North Pole, South Pole. You guys get it, right? Hey, low Earth orbit. Where's low Earth orbit? Like, if you guys had to guess, low Earth orbit, like International Space Station. Is the International Space Station revolving around the Earth right about here? You guys think going right around? Okay. If my drawing's kind of to scale, is that pretty close to scale? Yeah, that's pretty close to scale. Right, that's about where the International Space Station is. Okay, and for International Space Station to be in orbit, remember we figured out the orbit Earth, I should say low Earth orbit, is about 7907 meters per second. You guys remember this from last week? Okay, so if you figure out the circumference of the Earth and you do this orbital speed, put it all together, how much time does it take International Space Station to go around the Earth? Does anybody know? You can calculate it. It's about 90 minutes, right? It's about an hour and a half. It takes about an hour and a half. Right? So astronauts on the International Space Station go around the Earth once every 90 minutes. Okay. Now, how about the moon? The moon is way the heck out here. This is not the scale, but you guys get it, right? The moon. Guys, how long does it take the moon to go around the Earth?
Well, from what I read on the Luna 1 thing, 28 days.
Yeah, about 28 days. Right. I don't think it's exact, but you guys get one month, right? Moon, month, same root word, right? You guys get it, right? Okay. By the way, 7907 only refers to the satellite, not the moon. The moon's going slower, right? It's further out. Okay. Hey,
Also, it needs to travel a much longer distance.
that's true too, right? Yeah, it's got further distance. It's going slower. Yeah, it takes more time. Okay. Do you guys think that there is a place you could park a communication satellite so that well, how about this? What if there was an orbital period of 24 hours? Right? Do you guys imagine probably right about here, it could take like 24 hours to go all the way around? Right? And if that's true, what would that look like from the surface of the Earth? If you're looking up at that satellite, hey, there's a satellite. What would that be? It's going to stay above the same point above the Earth's surface all day, every day. Yeah, right. Right. That's called geosynchronous. Right. Let me pause this. All right, recording is resumed. Oh, Yeah, Miss Armstrong's?
Yeah.
Oh, do you know where her room is? Oh, hang on, let me look that up. Pause this. All right, recording is resumed. Okay, so, okay, I think you guys get that, right? Geosynchronous has been like lined up with the Earth, like in sync with the Earth. Right, let me flip my screen over and got one more cool thing I want to show you guys before we pick off this Kahoot, and that is, here, let's start with this one. Okay, Lagrange points. So, do you guys imagine that there could be some point, for example, between the sun and the Earth, where gravity kind of cancels out? Right, sun pulls to the left, Earth pulls to the right. You know, it's a wash. Okay, would that point be closer to the sun or closer to the Earth?
Probably close one.
Yeah, closer to the Earth, right? Because the sun's so crazy massive. Yeah, closer to the Earth, right? Now that's not a super stable point. It's kind of like trying to balance a ball on top of a roof, right? It's going to roll off one way or the other, but you know, it's kind of a wash at that point. Okay. Now that would be the only sort of wash point is in a state in a static solar system. But there we've got orbital mechanics. So, oh yeah, go ahead. Yeah, go ahead. You guys see this point L2? Do you imagine there could be a point around that L2 that the Earth is pulling you to the left, the sun's pulling you to the left, but because the Earth is orbiting around the sun, you could also be sort of in an orbital path following along with the Earth, and you could look down. You're like, I'm about to crash the Earth. You never actually get any closer, right? In fact, you guys remember James Webb Space Telescope? It's been in the news a lot. They launched it less than a year ago. It's been sending back all kinds of cool pictures. That one's actually in orbit around L2. Okay? Now, if L2 exists, then there has to be an L3 sort of by logic, by symmetry. Right? Before sent space probes, so before 1957, there was a lot of speculation that there might actually be another planet out here, but we've looked. There's nothing going on out there, but could have been, I guess. Then years later, along comes a guy named Lagrange, who these points are named after. He does a bunch of fancy math and realizes, hey, you can make an equilateral triangle between two masses. So two heavy masses, equilateral triangle. Okay. L4 and L5, there are also points of gravitational stability. And I can show that even better with this animation. Look at it. So here's our solar system from above. The sun's right at the middle. Right? You guys see this point going around? That's Jupiter. Right? You guys see all those pink dots? Guess what those pink dots represent?
Lagrange points of the universe.
That could be helpful, right? How about asteroid belt? Right? Do you guys think the pink dots are like asteroids in the asteroid belt? Right? And you're right that you can see the Lagrange points. Right? Because see how it's kind of triangular-ish? Right? So see this point right here? Right? You guys know that by far the two largest masses in our solar system are, well, the sun is like 99% of the mass of the solar system, but the second biggest by far is Jupiter. Right? So we've got Jupiter and the sun, and here's the L3 point right here from Jupiter to the sun. I'm following around with my mouse cursor, right? Mouse cursor. You guys said? Right.
And it's the opposite of Jupiter.
Right. Yeah, kind of opposite of Jupiter. Okay. How about those green patches? Do you guys see how those are like the L4 and L5 points from Jupiter to the sun? They make equilateral triangles. Now, the green patches are asteroids. They're called the Trojans and the Greeks. Yeah, remember back for mythology. All right, so there you go. There's the Lagrangian points. All right, you guys ready for Kahoot now? Kahoot time. All right, so back to here. Again, these are the same conceptual questions that I gave you guys on that half page. I'm not picking up everything, it's just extra notes for you guys. But these are some really solid questions. So yeah, you might see some of these on your quiz coming up. All right, so here we go. Newton hypothesized that the moon there you go. Those are all true statements, right? It's attracted to Earth, but it also has a tangential velocity, so it's like falling around the Earth. There you go. All the above. True statements. Tramalfadorian. Monty, John Gravy, Lindsay, Alexis. If the mass of the Earth increased with no change in radius, what would happen to your weight? Yeah, your weight would also increase. All right. So just in case you missed that, you guys are doing pretty good compared to earlier. All right. Just in case. You guys remember? Now this that expression can solve that question for you, right? But the picture I can modify a little bit because instead of like two objects floating in space pulling together, okay, what you do instead is just do like a planet and a person at the surface, right? Right. And then, but it's the same formula, right? M, and the gravitational force of attraction, equals constant mass planet, mass of you, by. Here, I'll do raise planet squared. How about that? All right. Yeah. All right. Yeah. So if you increase the mass of the planet, then you'll also increase the gravity force at Monte Lopez to the top. If the radius of Earth decreased, I'll also say what would happen to your weight. Yeah, your weight would also go up. Now, this one takes a little bit deeper thinking. So let me flip back over here, and I can still back it up with the exact same expression now. Okay. So another way to say that is like if you crunch down the Earth, right? Because if the radius is decreasing, but all the masses are staying the same, it's not like we're crunching down the Earth, like right? Now, if you're standing on a scale during this process, right, you would actually notice that your weight went up. You would actually get heavier. Now, why would that be? Right? Well, isn't this R getting smaller, smaller, smaller? Guess what happens when you divide by smaller numbers? Does it blow up overall bigger? Okay. How about this? What if the original force was like, right, so like 100, or no, let's do this. Let's do 24 units. And let's say R squared comes out to be like 8 units. I guess it'll be like 3, and then, well, force could be like newtons, like 3 newtons, for example. Okay. But what if you took, same masses, so nothing in the numerator changes. Right, so that's all the same. Okay. But now you make R a little bit smaller. Again, we're like crunching this down. R is getting smaller. And let's say that R squared comes out to like this many units. What's that equal to? Okay. You guys see an inverse relationship? So as the radius gets smaller, the overall force gets bigger. Get that? Ooh, interesting. Right, that's the answer to that one. Monte Lopez, the lead. Gravitational force between two massive spheres. Yeah, those are all two statements. It's an attraction, depends on how massive, but also inversely related to the square of the distances between them. Okay, more distance, less force. All right. All true statements. Monte on fire. Two objects move toward each other. As they get closer, what happens to the gravity force between them? Yeah, it's going to increase, right? So this is the inverse square law, right? So less distance is more force. Flip over here real fast. Right, so yeah, as they get closer, see if they were crazy far apart, it'd be a very small force, but as they get closer together, more and more force, right? So as you decrease the R, you're going to increase the F, right? Which is kind of a lot like what we just did with this, right? Pretty similar idea. Gravity force between two spheres is 100 newtons. What if you double the distance? ooh, yeah, you would have a quarter of the force. Guys, double the distance is a quarter of the force. Okay? And a quarter of 100 is 25. Okay? So let me switch over here and let's look at this one. So this could be the setup part, right? Two spheres, distance. Right? We're going to change the distance, see what happens. Okay? We're going to double this distance. Okay? So we got force. Let's say the original force is just plain G M M over R squared. Yay. Okay. Then we're going to have a new force. So I'll do F new. Okay. And that's going to be, G is the same, the M's the same, the other M's the same. Let's go ahead and double that R. And don't forget it's being squared. Okay. Hey guys, what is the factor of 2 squared? Like 4? So like M you could pull out in front, right? G M M over R squared. Okay. And you guys see how that, we call it original force. That right there? So the new force is a quarter of the old force. Okay. If the old force was 100 newtons, a quarter of 100 newtons is 25 newtons. Okay. That's the inverse square law. If you double the distance, you get a quarter of the force. Young baby, on fire. Force of gravity is greatest on you where? Yeah, right on Earth's surface. Okay. Let me switch over real fast just to remind you in case you don't remember this. Okay, you guys remember earlier in class doing this right here? Okay, saying where's your weight at different places? So right on the surface, you weigh the most. Okay. And as you tunnel down, you weigh less, and as you take off from rocket, you weigh less. You guys remember that? Okay. All right. Lunar month, about 28 days. What if the moon were closer to Earth? Then what would be its orbital period? Closer to Earth. Yeah, less than 28 days. Okay. Captain Kepler would have loved this question because Kepler thought about this type of stuff, especially his third law of motion, right, for orbiting. Right? And so further away you are, the more time it takes. Right. Kepler nailed down that relationship. Oh, whoops. There we go. If you're 400 newtons, stand on top of a ladder so you are 1 Earth radius above Earth's surface. So haven't you effectively doubled your distance from the Earth, from the center of it? Now how much do you weigh? Oh, yeah, it should be a fourth as much, right? So see, again, if you double your distance, you should get a quarter of the force. A quarter of 400 is 100. Let me switch over and show you guys this story. All right, so here's the setup. Here's mass of Earth. Here's your mass. Okay. There's some radial distance between the two of you. I'll call this capital R. Okay, so we got that. All right. So then the force of attraction is like this expression you guys see over and over. But now we're going to go up this ladder. It's a crazy tall ladder. That is also 1 Earth radius tall. Oh, it's also another capital R. Okay. So if you're standing near the top of this ladder, you guys see from here to here would actually be 2R. Right, you guys see that? R plus R makes 2R. Right. So you've doubled your distance from the center. From here, from the bottom ladder to top ladder, you double distance. Hey, if you double that R, isn't the new force equal to G M M? I should say top, right? Force top. How about that? 2R quantity squared. Okay. 2 squared. That's 4. Pull that out in front. The new force is 1/4 of GMM over R squared. Okay, and GMM over R squared, well, that was the original force, right? So if you weighed 400 newtons down here at the surface, this person weighs, where's my teaching? This person weighs 400 newtons at the surface, right? Standing on a scale, that's a force, gravity force. Okay. This person up here only weighs 100 newtons, right? Because it's 1/4 as much, right? Hey, could you guys do that in reverse? What if you started off with the guy at the top of the ladder? Say, okay, 100 newtons weighs up here, right? 100 newtons gravity force straight down, and then climbs to the bottom of the ladder, okay? You cut that distance in half. Okay? Guys, if you cut your distance in half, shouldn't that be 4 times the force, which would be back to your original 400? Right? Is that true? So you guys follow that. We're about to find out. Got Young Gravy, we got Tramalfadorian on fire. Martin Lopez, Alexis. Suppose gravity force between 2 spheres is 100 newtons, and you cut the distance in half. Now what's the new force? Yeah, 400 newtons, because that's what we just did, right? The last 2 questions, aren't they just exactly the reverse of each other? Well, mathematically they are. Right? The story's a little bit different, but it's the same idea, right? Okay. So if there's a 400 newton force between here and here, you double your distance, and now there's only 100 newton force. There's twice the distance, 1/4 of the force, right? Well, then the reverse, you can go the other way, right? So if it's 100 newton force here, and you cut your distance in half, well, now you're back to the 400 newton force, which is the answer to that question. According to Newton's laws, a rock and a pebble will fall at the same acceleration in a gravity field. True. Because why? Big old rock, little tiny pebble. Why did they accelerate the same? Free fall. Yeah, the ratio of force to gravity, or sorry, force to mass is the same. Here, you back this up with an equation real fast here. So they weigh different amounts. There's weight is the gravity pull, the weight's different. Okay. Do you guys remember how I've been calling weight mg? I've been labeling it this way on all the free body diagrams, haven't I? Okay. This is mass times gravity field. It's 2 variables multiplied together. Okay. What if you solve for that g? Wouldn't g just be weight divided by m, which stands for mass? Okay. Weight per mass. Okay. Maybe if you have a bunch of objects, they have all unique masses, which is inertia. Okay. They have all unique weights, which is a force, but the ratio of weight to mass. Okay. Yeah, that's your free fall gravity, which at the surface of Earth is about 9.8 meters per second squared, and different planets it'll be different. But for one planet, all objects will free fall at the same rate. Tramalfadorian still on top, on fire. The value of acceleration due to gravity. Yeah, there you go. Yeah, so all the above, those are all true statements. All right, you guys got it. All right. Gravity field strength at the center of Earth. Yeah, 0. Remember we talked about that? If you're at the center, every grain of sand pulls you a different way, it all cancels out. All right. The 0 at the center. Oh, we made a whole graph out of that, right? Whole graph out of that. Here, I flipped over real fast. You guys remember what this graph looks like? So at the center, you weigh 0. You guys remember that? That's that point right there. Oh, whoops. Tremel Fedorian, Monty Lopez, Young Gravy, Alexis. E. If the sun were to collapse into a black hole, what would Earth do? Okay, think about orbital mechanics. Does the mass change? Does the distance change? Does the orbital speed change? Does anything change? Okay, so from an orbital mechanics point of view, everything stays the same, right? If the mass is the same, the distance to the sun is the same, or now black hole is the same, right? The orbital, right? So nothing changes from the orbital mechanics point of view. So it's just going to keep going around. It's just going to keep going around. Oh, Monty Lopez taking top spot. Okay, I have to speed this up a little bit. Guys, when a star collapses toward a black hole, doesn't its mass stay the same? So everybody's picking the yellow one, right? Everybody pick the yellow one, right? Mass stays the same. Right, that's called conservation of mass. You guys remember conservation of mass, right? In order for tidal forces to be significant, there must be a relatively large distance between. Here, I'll tell you guys this one too. Okay. It's not the blue one. It's not the body causing tides and body. It's not the total distance. Okay. It's you want to look at the proportional distance opposite sides, right? Isn't that what we just talked about at the beginning of class? Right, you guys remember that, right? If the radius of Earth was half of what it is now, but the mass was the same. Okay, so we crunched down Earth really tiny. Guys, what is 1/1/2 squared? Is that 1 divided by a 4th? And what is 1 divided by a 4th? Is that 4 times? Right?
Yeah.
Right. And what is 4 times 10? 40? Yeah, 40 meters per second squared. It's actually a shade less than that, right? So 4 times 9.8 meters per second squared gives you the green one, right? Right.
Oh my.
A circle is a special kind of. You guys remember making those ellipses with the string and the pencils? Right? Ellipses. Right? You put the 2 foci on top of each other, you have a perfect circle. There you go. Circle's a special case of ellipse. Object placed geometrically halfway between the Earth and the Moon. That's going to fall towards the what? So you guys said the Earth, right? Yeah. Right. Now there is no one point between the Earth and the Moon, but it's closer to the Moon. Right. So geometrically halfway, you're looking for the larger mass and probably more force. Right. And last question: early bird communication satellite hovers above the same point above Earth's equator indefinitely because why? You guys said it has an orbital period of 24 hours. There you go. Orbital period 24 hours. You hover above the same point over and over. Okay, but we talked about that earlier too. Okay. All right, with the bronze, Young Gravy. With silver, Monty Lopez. And the gold, 1820. Tremel Fedorian. Right, you guys have a great rest of your day. Oh, runners up, Alexis and Eve. See you guys tomorrow.